flattening problems.
Thank you very much for introduction. So first of all, I would like to express my thanks to organizers for giving me a chance to talk here. And the title is Kite Property and its applications to continuous flattening problems. And the first, this is a list of my talk. And the first is the motivation of this research. And second is an open problem on continuous flattening of polyhedra and known results. And the third is the kite property. And the fourth is applications of the kite property to foldable helmets and boxes with thick panels. And the last is the future work. And now, so there are so many foldable products in our daily life. For example, so foldable umbrella, airbags in the car, and tents, foldable chairs, foldable tables, so on, and foldable helmets. And I will talk about foldable helmets later. And so are there foldable products with completely closed polyhedral shape, especially made of thick panels. So this is a motivation. And now here is an open problem. Can we flatten a polyhedral piece of paper? It means we can fold by creases and without tearing nor stretching. So this problem was proposed by Domain Review 2001. And the flat folding of a polyhedron means folding by creases into a multi-layered planar shape. So I brought here a container of the juice. This is a box. And after we drink out, usually we may be flattened here. This is a flat folded state, we call. And from the original box, is there continuous motion? This is a question. So without tearing, without cutting, it's okay to fold like here. I put a crease here. So fold is okay. We can fold by creases. This is a question. So now, precisely definition is as follows. A continuous flat folding motion of a polyhedron P is a continuous family of polyhedra PT, which satisfies three conditions. First one is for each P, PT is isometric to P with respect to the intrinsic metric. And the second is from T to the compact set PT is continuous. And the last one is P0 is P and P1 is a flat folded state. This is the definition. And so there are fundamental theorems. Cauchy's rigidity theorem says any convex polyhedron is rigid if its faces are rigid. So only transform to the congruent polyhedron, so by continuously. So if we take off the assumption of convexity, then Connelly showed the counterexample. There is a flexible non-convex polyhedron whose faces are rigid. Example. Just he showed the example which can be flexible. And so, however, Savitov proved the volume preserving theorem. It says any polyhedron preserves its volume under flexing. So it's called the Villot theorem. Now, the volume of polyhedron, if we think about that, decreases to 0 under flattening. To do this, some of faces should continuously change their shapes by creases under flattening. It's necessary. So we call those creases moving creases. The problem is find moving creases from the box to here. So somewhere we have to change the shape of face. This is a problem. And this is the list of the known results. And the first four, so related to convex polyhedra. And the last two includes some non-convex polyhedra. And there are three methods here. And now the convex case is completely solved by using the two methods. And one is called Katrogas and Alexandrov's gluing theorems method. And the other one is called straight skeleton and orderly squashing method. And both, usually we have to move the creases almost all over the surface. And if compare this, Kite method is useful for applications because regions of moving creases is pretty small. So I would like to introduce the Kite property briefly. And so Kite is like this, and the same length and the same length here and here. But I want to use a rhombus because it's simple to show. So here is a rhombus. Yeah, maybe here. And without folding the four boundary edges, we can adjust the distances of two pairs of diagonal vertices here and here by folding like this way. Then we can change the distance. Not one by one, together we can do it. This is, we call this figure is a folded kite. And then if we give a distance, two distance here and here, then we can find the unique point Q here. And we can get this. And continuously we can go to some other folded kites. So this is we call the kite property, and for this is a general case, but I want to skip detail. But this generalized to the more cases. And now I would like to go to the application for foldable helmets. Here I made a model. I used the cover of the booklet of this conference because it's so beautiful. I want to keep this as a memory. So I use this. I folded this by the accordion folding, just the accordion folding. Then we can get this shape, right? And I put the staples here for gluing, just the corner. Then if cut off the corner, you will see the figure is the same as the bottom left figure. This is a figure. And if we open this here, like here, then how about this? So, like this, if we open it, this, then we can get the cover of a helmet. Because in Japan, we have a lot of earthquake. So it's very, very important to invent a foldable helmet. So we worked. And so where is the kite property? Then now I want to show the right side. Please look at the right side. And maybe you can see here, so please look at each piece. Then here is a triangle. Please consider the congruent triangle here. Then you will see the rhombus. Then, so first, the rhombus is like this shape. Can you see? This is a top panel, and this is the side. And then finally, it will go to this. But from here, from this to here, so by using the rhombus property or kite property, so there is a continuous motion. Then by the calculation, so we can get this is okay. No, it's okay. Then we can get the region of the moving creases precisely. And the shaded parts are for moving creases, very, very small. So therefore, we don't need to cut off because a little bit is flexible. This is a paper. So moving creases, we don't need to cut off. So here, here, and here, and here, moving creases are here. And so now this is already in market because we worked with the cardboard company called HUN-REN. And because cardboards are flexible a little bit, so the cover is originally came from this design. And this is not strength enough. So we added inside, attached the foldable honeycomb structures inside, so to improve the strength. So this clarify the regularity for the safety. Now so in market for sale. And so now next application is to foldable boxes of thick rigid panels. And because of thickness, we cannot do like this. Because the thickness, we cannot fold by creases. So this is a little bit flexible, so we could do that. But thick panel means we cannot fold the panel, which means we have to cut off the region of moving creases to avoid something, right? So therefore, the necessary to have a hole. So hole small is good. This is the first request. And the second is transformation is simple. And the top and the bottom faces are rigid. Just I put those requests. Then, so forget about the thickness. Go back to the case of the made of the like a paper. Then how about that? So keeping the top and the bottom face, no crease, and if we push all four side faces, then we can get flat folded state. This is the top, and or maybe we will push the side in but for this side push out the combination, then also we can get like this flat folded state. If we push all out, also we can get a flat folded state. And so there are three types, and we can reach there by using Kite property continuously. And so if we compare the area of the regions of moving creases for those continuous motions to reach those flat folded states, then if we push in all sides, then it means fold into halves all four faces. Then they will have a collision. And so at that time we will use the Kite property to fold the one of the face each time. Then creases are shown by red colors. So the first case, those four triangles are the region for the moving creases. But if we push two faces in and push two faces out, combination, if we use this, then we can avoid not much collision. So therefore, only very small region is used for moving creases. The area of case 2 is almost 1/6 of the case 2. So we will use the second one. Then remove the region of the moving creases or replace those parts by flexible materials. And we want to put a thick panels there. Then how many panels do we need? Just count. So 1, 2, 3, 4, 5, 6, and each this side have 1, 2, 3, 4, 5, 6. 6 times 2 and plus 2 times 2 plus 2 times 2. Therefore, 18 panels we need anyway. So 18 rigid panels with uniform thickness are assembled by hinges. Hinges means the rotation axis. We need to rotate the panels. And then bold lines show the place put hinges here, here, here. But we need a little bit more work because if we look at this panel here, this point, degree 4, 4 panels meet at this point. This point is usually called Bennett linkage. I want to skip the detail, but this is very popular in mechanics. So this is degree 4. We use the Bennett linkage. It means, so set off the position of hinges. More clearly speaking, so I attached the quadrilateral poles like this. These two, so just behind the trapezoidal panel. There are 2 trapezoidal panels. So I brought some small model here, and on the back I put this. Then it will go to here. But anyway, so here is a simulation model. So this is a joint work with my colleagues and his students. And now, please look at, if we push from the top, so it's stable because of I put the supporters by hinges. But if we push from the side, then here is a hole to avoid a collision. And the hole will close and getting smaller and smaller. And if we push one time from the bottom, automatically it's go to down. And we can get flat folded state. And now, so here, the distance between the diagonal points here and here by using a Kite property, this distance is getting longer and bigger. This distance is getting smaller and smaller, but the distance is so getting bigger and bigger. And this is just a combination distance. And now you can see the hole some here, and finally we can reach to the flat folded state, I hope. Yeah. Now, so continuously we reached. So if we look at from the side, so maybe you can see the Bennett linkage, how it works. Here is Bennett linkage. Oh no, I have to go to the next one. Yeah, here. So here is Bennett linkage because 2 trapezoidal panels, so necessary to attach the something to put the hinges. So maybe it's easy to explain by using these 2 panels. We'll go between these 2 trapezoidal panels. So need some space to put into here. To do that, we need some extra things here. And just the middle, here is a hinge. So the rotation of these trapezoidal panels is the rotation axis here. Then we can reach to the flat folded state, so completely, and can go. Yeah. So I made a model by using carbon. Yeah, first, anyway, and it worked. So I asked the students to make the model by simulation. And now, so this is applicable to n-gonal convex prism with small heights, so strict directly. But how about others? So regular tetrahedron, we know how to get the flat folded states, and we know the region of the So moving creases area, very small. And also, we know for the regular octahedron, very, very small area here. And also, we know how to flatten the dodecahedron to get to the platform state like this. We know that. But the problem is, so where is the position of hinges? And the second is we have to improve the stability when we unfold it. We need stability of this. So there are two problems. That's the future work. Okay. Thank you very much for your attention.